Hi gang, Dr. Stevens here with another quant video, this one on the recipe error. When formulating linear programs, there's a very tempting trap that a lot of people fall into, that of basically trying to write a constraint that looks like a recipe. That's what we're talking about today, how to recognize it, how to avoid it, and how to do the right thing rather than the wrong thing. So to get started, let me talk about chicken. That's my picture of a chicken. I am no particularly great artist. In fact, I don't just want to talk about one chicken, but I'd like to talk about a bunch of them. Why? Well, in part because I'm kind of hungry. Sorry, but it's true. As you know, one of the things that goes on is that we take chickens and we prepare them, and I won't go into details here, but we get some tasty morsels. Let's just say we start with chickens, and then some magic occurs, and then we have stuff to eat, like chicken wings, and chicken legs, and chicken breasts. What I'm interested in is the quantities of these things that we're talking about here, and how they're related. If I let chicken be the number of chickens that we start with, and then I let wings be the number of wings we end up with legs and breasts being defined similarly, the number of breasts and legs we end up with, then how are these quantities related? What's the math that talks about this stuff? Well, here's some advice you might get on this problem. It's easy. A chicken gives 2 wings and 2 legs and a breast, so the equation is chicken equals 2 wings plus 2 legs plus a breast, and we're done. Unfortunately, while this advice looks attractive, it actually comes from the evil demon of quant deception. The math that we've just written here is entirely and completely wrong. It is an example of a recipe constraint, which says that if you take these ingredients and put them together, you get one of these things, or conversely, that one of these things can be decomposed into these parts. There is no such thing as a recipe constraint, and that's why we call this the recipe error. What's wrong with it, though? Well, imagine the simplest case, where we take one chicken and process it to get 1 pair of wings, 2 legs, and 1 breast. Now, if the math that we've just written is correct, then when you take the values for these variables, namely 1 chicken, 2 wings, 2 legs, and 1 breast, and stick those numbers in the equation, sticking these numbers in that equation, the result has to be true. Doing this, plugging in numbers to see if they work, is called validation, and it's a really great way to see whether you've written nonsense when you're writing a linear constraint. Let's try it here. Plugging in the numbers that we've got gives us 1 equals 2 times 2, plus 2 times 2, plus 1. That is, it says that 1 is equal to 9. There's a technical term for answers like this in mathematics. They're called wrong. If you don't think so, I'd like to borrow $9 from you today, and I'll pay you back $1 tomorrow. I'm pretty sure you're not going to be cool with that, and you shouldn't be. So there's definitely something wrong with this constraint. Here's another way to see it, which leads to the issue of mutant chickens. Remember that the numbers that appear in a constraint are supposed to answer a question. Specifically, the coefficient of a variable that the coefficient that a variable answers in the linear expression always is this question: if the variable goes up by 1 and no other variable changes, then by how much does the thing we're talking about, the thing underneath, increase? Let's try that with our current example. Here's our equation. And no doubt about it, the left-hand side of this constraint is measured in chickens. Because the two sides are measured in the same units, that means the right-hand side is measured in chickens as well. So what's that 2 in front of the wings variable saying? Remember, the coefficient tells you how much the thing underneath goes up when the variable goes up by 1. So let's give that a whirl here. 2 wings says if wings goes up by 1, the thing underneath, chicken, goes up by 2. That is, it says we get 2 chickens for every wing. We've got the same problem with 2 legs. The coefficient rule says that means that if legs goes up by 1, then the thing underneath, chicken, goes up by 2. Again, apparently every time we've got a leg, we've got 2 more chickens around. Breasts is a little bit different. If breast goes up by 1, the math says that chicken also goes up by 1, and that part at least is correct. But the rest of it's garbage, unless you happen to live in a place where chickens look like this. As you see here, we have 2 chickens. Every time we get 1 wing, we get 2 chickens. Every time we get 1 leg, we get 2 chickens. If chickens look like this where you live, please move away from the nuclear reactor. All right, so if all that's wrong, then what's right? Well, the key is realizing this program only has one independent variable. By that, what I mean is if you know how many chickens you start with, you know everything. So the variables legs and wings and breast can be defined solely in terms of that one variable, chicken. They're what are called auxiliary variables. Now, the deal with auxiliary variables, variables you don't really need, is that you can always use them anyway, but you must have an equation, an equality constraint, that tells you how to compute them. So that's what we need here. An equation for wings, one for legs, one for breasts. Because there's only one independent variable, our templates in each of these cases is going to look very simple. So many chicken plus so many more. And now we'll use the coefficient rule properly to figure out what these numbers should be. Look at the wings constraint. We're looking for the number of wings. The question we ask is, if chicken goes up by 1, by how much do I increase the number of wings? The answer will obviously be 2. One more chicken gives you 2 more wings. The constant terms found by setting all variables in the problem equal to 0, that would be setting chicken equal to 0, in which case you get no wings. Don't butcher any chickens, you don't get any wings. Same argument for legs now. If chicken goes up by 1, by how much do I increase the thing underneath, the number of legs? Answer, obviously, 2. And again, if you process no chickens, you get no legs. Finally, breasts. If chicken goes up by 1, by how much do we increase the number of breasts? Well, we get 1 breast for every chicken, and if we butcher no chickens, we get no breasts. So there's the math we want. Clean it up a little bit, it looks like that. And it really is right. It says, for example, that if you want to know the number of wings that you're getting, take the number of chickens you start with and multiply it by 2. If you process 10 chickens, you're going to get 2 times 10, or 20 wings. Absolutely correct. Notice that the expression for wings and legs are the same. That doesn't mean that a wing is the same as a leg. These are numbers. It does mean that the number of wings that you get from processing chicken should be equal to the number of legs you get, and that's also correct, with breasts being only half that big. So that's the correct math and the way that you can think about it. But the big takeaway from this is simply this: there is no such thing as a recipe constraint. Thanks.